Okay, so let me start by first advertising our workshop. We are organizing together actually with Domonkos and Balas a workshop on deep learning for recommender systems at this year's ACM Recommender Systems Conference in Boston. So if you have any nice papers on deep learning for recommender systems, you're welcome to submit them. We're going to have a look at them and maybe we're going to accept them. So let's go to my slide deck. Here we are. So my name is, first of all, my name is Alexandros Karatzoglou. I'm a senior research scientist at Telefonica Research. And I'm going to talk a little bit about deep learning for recommender systems. This is more like an overview talk. I'm going to try to give you a bit of an introduction to what deep learning methods can do for you and what they can do for recommender systems, right? So a little bit about what we are doing at Telefonica. We are sort of like between pure research and industry, right? We do research on machine learning and other topics, networks, systems, mobile computing, etc., etc. And we try also to apply this research in business units at Telefonica, right? So we publish papers, etc. And we are a team of about 15 to 20 people with PhDs in all these areas. So why deep learning? Why is it so? Let's say, why is there so much interest in it, right? So there are many reasons. Actually, I think there are probably two main reasons why this happens at the moment, right? These are the results from another challenge, not the Rex's challenge. It's called the emergence challenge, which is about recognizing objects on pictures, right? So it's a challenge that runs for many years. And this is basically the error achieved by the best performing method during that year. And you can see that...
Excuse me, may I ask to use the mic because we record you.
Okay, yeah, so I cannot move a lot? Okay, sorry, okay. So these are the best performing methods for each year. And you can see that after 2012, when deep learning techniques were introduced, there was sort of a big jump in performance, right? These are error rates, so the lower the better. And what is actually quite interesting is that this red line there represents the performance of humans on this task, right? It represents the performance of humans on recognizing what objects are on various pictures. And you can see that the actual solution of 2015 outperforms humans already, right? So we have an algorithm that is better in recognizing images than actual humans. So this is quite important milestone for machine learning, and it sort of showcases the power of deep learning techniques. I think the second reason why deep learning has become so popular is that it actually makes machine learning a little bit easier, right? Not a lot easier, but a little bit easier. So if you look at how machine learning was performed, let's say before the deep learning sort of techniques, and in particular, let's say image classification, right? We had sort of an image. We had to think of features that we could extract out of this raw data, the raw data of the image, compute these features, and then feed these features into some kind of classifier to detect what kind of object there was on the picture, for example, right? So there was a lot of handcrafting of features, sort of a lot of engineering involved, right? And a lot of the papers, let's say in this computer vision conferences, were actually about finding good features to extract from these images. Now with these deep learning techniques, we actually can automatize the feature extraction process. We can actually feed these algorithms with the raw data of the image, and they extract the features for us. So we are kind of one step closer, one small step closer maybe to true AI in some sense, right? So because we automatize a process that was done in the past manually. So now we basically take the raw data and we can feed it directly into a deep learning algorithm. I will talk a little bit about what kind of deep learning algorithms these are. And we can get sort of the class of the object. No? So you probably know about this more or less. So deep learning techniques were inspired by the way the human brain works. And there's an analogy here. It's a little bit like how people started to how people sort of thought about flying, no, they tried to emulate the birds first, and you can see this is actually a model of a plane that was constructed in France. It never flew, of course, but it was inspired by a bat, right? So, and this was actually about 6 or 7 years before the brother Wrights actually made the first flight, right? So even up until the people started actually flying, they still were trying to emulate birds, no? And if you look at the planes nowadays, they still sort of look like an abstract version of a bird, right? There are these wings and there's this kind of central body in the middle, right? But, you know, there's these 2 jet engines there as well, right? That help the process. So, and something similar is happening actually with deep learning. The first sort of deep learning neural networks, let's say, were really biologically inspired. No? People were trying really to emulate what's going on in the brain. And the more sort of people moved away from this paradigm, the more successful sort of these methods started to become. No? And basically the main idea behind deep learning and neural networks in general is that we have an abstract version of what is called a neuron, which is inspired by the brain. And this neuron basically takes some kind of inputs, which is our data, multiplies these inputs with some weights, sums up this weighted average, essentially, right? With this transfer function, passes the result of that through an activation function, which in the past used to be the sigmoid function, and gives out an output. In some cases, these neurons have also states, and the states depends on the output, right? It can be, the neuron can be on or off, but in most cases, the neuron just outputs a number. That's all you need to know. And this is the basic computation unit of a neural network and deep learning method, right? And we are going to see what sort of changed during the last years. Not much, but some things changed with respect to these neurons. A traditional sort of neural network is essentially layers of these units, right? Several layers of this neural units. And at the first, usually we have the input, the data, right, coming in, which is multiplied by all the weights of the corresponding units. Then these units have an output that is then multiplied by the other weights of the second layer units, et cetera, until we get some kind of output layer, where in the output layer we can compute the probability that this data that we had in the input belongs to a certain class, right? In this case, in our output layer here, we have 4 classes, let's say. Yes. So we compute the probability that this data point belongs into one of these 4 classes. Now, this is a typical feed-forward multi-layered network. And it can also be seen as a sort of type of nonlinear function, which is essentially a series of matrix vector operations. Okay, and when we say that we are learning this model, right, the learning process is essentially finding out which weights we should have there for the neurons so that they perform the tasks that we want them to perform, right? So when we learn these deep learning networks, essentially what we mean is we're learning these weights of these neurons, which are usually represented in these big matrices. And the way this is done typically is with stochastic gradient descent. I'm not going to go through the details. It's a very, very simple algorithm. Essentially, you have a objective function, right? Some kind of training error that you want to minimize. And you compute a gradient on this training error, and you take a step in the direction that minimizes the objective function, right? And this is sort of how this objective function looks like with respect to 2 model parameters. If your function, of course, is convex. In the case of neural networks, it doesn't look so smooth and it's not so simple. People still don't know why it works. It's probably looking a little bit like that, but it's very similar to kind of going down a valley with your eyes closed and trying to guess sort of which way to go down the valley in the fastest way, right? That's basically what stochastic gradient descent does. Okay, and So you just take a gradient and you do a step, and then you reach the bottom, right? So that's the main idea. And for this multi-layer feed-forward networks, there's a generalization of this technique of stochastic gradient descent, which is called backpropagation, right? You take this stochastic gradient descent and you apply it layer-wise to each of the layers of the network. This is basically what's backpropagation. And the reason why this is done nowadays, or the reason why NVIDIA is doing so well these days, is that this is basically it's a very heavy sort of computational intensive task, and there's a lot of matrix vector operations involved there. And the GPUs are really, really nice to do this, in doing this. They're really, really fast in doing these operations. So that's why people nowadays use GPUs to do deep learning. No? So this is basically, or let's say this was more or less a standard neural network that people also used in the 80s. And what you should know is that these networks in the 80s and the beginning of the 90s, they were not really working very well when they had many, many layers. And the reason was that, or it's believed that the reason was that there was something that is called vanishing gradients. And one of the reasons that these vanishing gradients occurred is that people were sort of so, let's say, attached to this this biological model of learning, that they were keeping sort of the sigmoid activation functions in the neurons, okay, in the units of the deep learning networks. And if you look at the sigmoid activation function, there's actually a big area where they're very, very flat, right? You see here, and basically in that area, it's very, very difficult to compute a gradient. Right? The gradient is very, very small. And this led to slow learning. This is also often referred as the getting stuck in local minima, etc. No? And along came support vector machines, which were nicely convex models, which you could train very easily. And what happened is that people sort of abandoned these neural networks, and we entered the second neural winter, it's called often, right? That people didn't do any research on these networks. And then recently, let's say in 2007, people came up with some new ideas. I'm going to go really fast through them. One of them was this rectified linear activation function. So they would basically replace the sigmoid activation function with this linear activation functions, and this helped a lot in the training procedure. On top of that, we had a lot more CPU power and GPU power. So we could go over many, many more iterations in the stochastic gradient descent algorithms. And suddenly, these deep layered networks could be trained again, right? And there were also more other tricks that are used, like dropout, where, for example, where essentially what you do is you take a network and you assume that half of its units are not there, right? Randomly. So you just drop them out at each training step. So essentially each data point sees a different version of the network. This also helps a lot performance. It makes the networks more robust, and it's essentially a way of doing regularization for these deep learning techniques, right? There were other things that came along, which was also, for example, training with mini batches. So when you now do this stochastic gradient descent steps, you don't go over each data point individually. What you actually do is you compute the gradients over 50 or 100 points, average the gradients, and then do an update step on your network. This is called mini batching. It also helps the performance, both because it reduces computational cost, and it also works as some kind of smoothing technique for the optimization method, right? Typically, in this modern deep networks, the output layer is a softmax output, which is some kind of generalization of logistic regression you can imagine. It just outputs probabilities over different classes, no? And we typically optimize some kind of loss function. The categorical cross entropy is a very popular one, no? There are other things that are coming along, like batch normalization, exponential linear units. You know, the literature on deep learning, it's almost hard to follow nowadays. There's like almost 3 to 5 papers every day with new ideas about how to train these networks and new network architectures. Adagrad is another sort of variation of stochastic gradient descent that is used very often in training these neural networks. And what this does is essentially it gets rid of learning rates. When you do stochastic gradient descent, you need to specify how big a step you do every time you take a step in the direction of the gradient. And this basically gets rid of that. It computes the step automatically. No? So let me now tell you one of the first techniques that was used, because we are here in a recommender systems meetup, right? That was used for recommender systems. One of the first sort of neural networks that was used for recommender systems. And I cannot say it was a deep neural network, it was actually a single layer of network, was the restricted Boltzmann machine, right? And the restricted Boltzmann machine is in its simple version, has 2 layers, right? The input layer, which you can see here in blue, and the hidden layer, which you can see there in red. And these 2 layers are connected with some weights, right? There's Wij weights there. Okay, and the way this network was used for collaborative filtering was that for a user, let's say this user, and a certain set of items, assume we have our item set is this 6 movies, okay? We matched, let's say, the movies to the input units and turned on or set to 1 the units for which the user saw the movie, right? You know, let's say in the Netflix price, typically a user would have watched maybe 20, 30 movies, and the total item catalog was around 17,000, if I remember correctly. So if we wanted to use this network for the Netflix price, we would have a visible layer of 17,000, and we would turn on or set to 1 only the units that correspond to the movies that the user has actually watched.
That would be a repeat factor?
Correct.
Okay.
Yes. So it's basically a one-hot encoding of the movies that the user watched, right? This is the input factor, right? And now what we do is with the weights that we have, we compute the hidden layer activation values. Okay, so we do a step up, right? We set these things to 1, the rest to 0, and then we compute the hidden layer, right?
But what is the output layer here? I mean, what are we trying to implement?
There's no output layer.
Whoa.
I'm getting there. Yes, it's some kind of unsupervised learning, but I'm getting there, right? So we compute the hidden layer, okay? And we set, and when we do this, we are computing actually values between 0 and 1. This is essentially the probability that these units are 1 or 0, okay? And given this values, right, 1 or 0 of the hidden state, we recompute the visible layer, okay? And now we have a set of values for the visible layer, right, that we can use to do recommendations, right? Because now all the values of the visible layer will be non-zero.
So it's like an autoencoder?
It's very, very similar in the sense, if you look at an autoencoder, you have 2 parts, right? The encoder and the decoder. Here, both the encoder and the decoder is the same network, right? This is a restricted Boltzmann machine. And the learning here happens essentially by taking the newly computed visible layer and computing some kind of loss function between the actual movies that the user has watched and what we are getting from this up and down sort of computations, right? So this was one of the first methods, actually was introduced very early in 2007, was used actually for solving the Netflix price, right? I think you probably also used it, if I'm correct here. And I'm not sure if it's very, very popular right now, right? I think most people nowadays use simply matrix factorization. but it was sort of one of the first neural networks to be used for collaborative filtering. So let me go now to another type of neural networks which are quite popular and are used in image processing, which are convolutional neural networks. And these convolutional neural networks are used a lot in classifying images, right? Retrieving images, detecting objects on images, segmentation, and are essentially a very important part of one of the most interesting sort of applications of AI nowadays, self-driving cars, right? So you have convolutional networks that detect the objects on the street and essentially help the car see what is around it. In fact, NVIDIA actually builds specialized GPUs for cars that are optimized to run these convolutional networks. No? And the way convolutional networks work is the following. Imagine you have an image, and you can imagine the data on an image as a three-dimensional array. What image data is essentially is a series of intensity values for red, green, and blue, RGB, right? And these intensity values are stored in three matrices. Okay, and a small image, let's say a 32 times 32 pixel image, would look like this. You would have a depth of 3 for the three colors, right? And 32 times 32 pixels. Okay. Now, what a convolutional network, so let's say the basic unit of a convolutional network is what is called a filter. And a filter has the same dimensionality as the image, in this case a three-dimensional array again, but it's typically much smaller, right? In this case, it's a 5 times 3 filter. And this filter has also some parameters in there, some numbers, you can imagine, okay? And what we do is we take these numbers, we take this filter, and we take in part of the image and multiply the numbers in this part of the image with the numbers in the filter, okay? We multiply this element-wise, and we sum them up. So we end up with one number, okay? And what we then do is we take this filter and we move it around the whole image so that we cover the whole area of the image, right? We slide it around, either horizontally or vertically, okay? And what we get for each of these sort of slices of the image is we get one number. Okay, so we end up essentially with another image that is a convolution of the original image. Okay, that's why these networks are called convolutional. Okay, and we can do that also with another filter. So we initialize another filter with other parameters. We do the same procedure, and we get another convolution of the original image. And if we do this, for example, with 6 filters, we're going to get again a three-dimensional array, but now it's going to have 6 layers of numbers, right? It's going to be slightly smaller, probably. And it's going to be a transformation of the original image, okay? We can repeat then the same procedure on this new convoluted image with new filters, right? And this is basically how you create a convolutional network, right? You initialize this kind of convolutional layers, filters, sorry, and for each result of these convolutional filters, you have a new set of filters, essentially a new layer of the network. Finally, after several of these layers, what typically is done is you take the final sort of convoluted image and you vectorize it, right? You just take this sort of array and you create a vector out of it, and you feed it into some kind of normal classifier, normal deep network, fully connected. And the way these networks usually work is that at the lower parts of the layers, the first layers, let's say, learn very simple features like gradients and edge detectors, etc., color gradients, edge detectors, etc. No? And the higher up you go in these layers, the more complex or higher level these features become, right? You can actually potentially see here at the third layer some kind of wheel kind of based structures, etc. Right? And so basically the higher levels of the network, the higher layers of the network learn higher level features. That's the way people think that these networks work at the moment. And these high level features are then fed into some kind of classifier, which typically is a normal feed-forward network, and then you get some kind of class out of it, right? So basically you have a detector, it detects sort of some kind of rectangular objects, wheels attached to it, so it's a car, right? This is the architecture of one of the most popular convolutional networks. You can actually go and download this kind of networks for many of the deep learning packages. It's available. It's trained on this ImageNet data typically. It's called the AlexNet. And you can see you have here the original image. I think there are 96 convolutional filters in the first layer, 256 in the second, etc., etc. Right? Up until you can see there the last convolutional layers are fed into a dense network, and then you get some kind of classification out of it. So let me do a small detour here, but notice before that you have here an image going into the network and some kind of classifier in the end of the network, right? But just before this classifier, we have some very dense representation of the original image. So we have a 4,000 dimensional vector that is fed into the final layer of the classifier, and this gives us the objects that are in this image, right? So we have a relatively dense representation of the original image in this last layer of this network, okay? Small detour now. Okay, how many people know about matrix factorization here? Okay, I can skip it, I think, then. Very good. Excellent. So you know about item features, user features, right? Okay, very good. So now again, let's go back to recommender systems. How can we use this amazing sort of technology here, these convolutional networks, for our purposes of recommending nice products to users, or jobs, etc.? Well, there was actually a quite nice paper published last year, I think, or this year. I'm not sure if it's 2015 or 16. And this is the main idea, right? You take exactly the convolutional network that I showed you in the previous picture, and let's say you have a store that sells some clothes, okay? And you take that convolutional network and you go over the picture of the clothes that you're selling, right? And you take exactly the last layer of the network before the classifier, okay? So you take this dense representation of the image, this 4,000 dimensional vector. Let me go back, show you again. So you, put here the image, and you take exactly these vectors here, right? These are 2048 and 2048. You concatenate them, right? So you have 4,000 something dimensional vector representation of the image. So you take that vector from the image that is on your catalog, and what you do is you do a small embedding of this image into some lower dimensional space, and you take the resulting vector and you append it to your item features from the matrix factorization, okay? And you optimize this, you optimize your user factors over this new sort of item feature representation, right? Which is let's say a sum of the item features that come from a concatenation of the item features that come from the collaborative filtering and the item features that come from the image of the product. So you learn the taste of the user both from his sort of collaborative effects on the data and the image that he's looking at, okay? And this seems to work quite well. And it's quite a relatively easy, so let's say, way of incorporating this collaborative filtering to incorporate this convolutional networks into a collaborative filtering algorithm. Okay. By the way, if you have any questions, feel free to stop me again. So another application of convolutional networks was for music feature extraction. Okay. Convolutional networks can be also used on audio. They are actually used frequently on audio. And the application here is that, well, you can do music recommendation with a typical matrix factorization, right? You take what you are listening to, what other people are listening to, you factorize this matrix, you get a profile for the user, profile for the items. It's quite boring, right? And it's actually literally quite boring because music is, I mean, if you know, if movies and everything is popularity biased, music is crazy popularity biased, right? Everybody just listens to the same thing. So it's like doing essentially popularity based recommendation. So to try to escape from this sort of popularity trap, you can actually go and use the content of the music, right? And the way to do this is to take some kind of Fourier transform of the MP3 files, right? And what you end up with is some kind of intensity map over frequencies that are contained in the music file, right? In the raw audio. And you can look at this as a kind of very long stretched image. And you can use convolutional network in the same way. You can use them over images. The only difference here is that you use one-dimensional convolutions, right? You take the convolution and you slide it over the time. Okay, so this is actually, I think, this was done at NIPS 2014 by Sander Dielman, Aaron van der Oort, and Schrauven. And what they did is they run these convolutional networks over the raw audio. And so first they did a collaborative filtering, typically matrix factorization type technique, right? So they computed the item features for the audio from the collaborative filtering. And then they took the raw audio and they tried to predict with a convolutional network the corresponding item features. So essentially what they did is they embedded the raw audio into the item space of the matrix factorization, right? And in this way, you can now compute similarities between items that are not listened very often by users, right? So you can actually do recommendations in the long tail. And on top of that, you escape the cold start problem, right? When you get new music, you can directly embed it into the item space of your collaborative filtering method. Okay, and this actually turns out to work quite well. If I'm not wrong, Spotify uses something like that right now in the production system, right? Okay. Another quite interesting application, which is doesn't have much to do with recommender system, but it's actually quite fun, is people use these convolutional networks to do art, right? There's some kind of way to do to take the signal of the neural network and modify a picture. For example, you can take a picture of a sheep, put it attached to a convolutional network, activate the dog class, and propagate the signal back. And what you get is something like that, right? So, and people use this kind of networks to do lots of interesting art projects, right? So they train networks on different painters and then take a typical picture and make it look like it was painted by Picasso or stuff like that. So this is quite interesting application of these networks. And so that's more or less the current state of the art in convolutional networks and recommender systems. And another sort of architecture of neural networks that is used we actually use that for recommender systems are recurrent neural networks. Okay, so what's a recurrent neural network? the main difference between recurrent neural networks and, let's say, standard neural networks is that now the units in the neural network have some kind of state, right? You have basically the same sort of the same weights that multiply the input to the unit, etc., no? But now on top of these weights that process the input, the network also maintains a state, an internal state, which is represented as a single vector of numbers, you can imagine, right? So a typical neural network looks like this. So you have here the input that is multiplied by some kind of weights. And now we have another vector here that is maintained inside the network that represents the state of the network. These type of neural networks are very, very frequently used with ordered data, with sequences of data. Think of audio again, time series, text, etc., right? Any kind of data which comes in a form of sequence. Okay, so and the data is fed in the network in a sort of sequential way as well, right? You take a first letter in a word, right? The second, you take a second letter in a word, third letter, etc., right? That's the way you use networks. And the way output is computed from this network is that the current state of the network depends on the input and the previous state, and the output of this network here depends only on the current state of the network. Okay, so these two equations essentially are a typical recurrent neural network. Now, what you need to know about this type of recurrent neural networks, which are often also called vanilla neural networks, recurrent neural networks, is that very often they fail. They don't work, right? The reason is that it's very, very easy to get vanishing gradients in this kind of neural networks. So basically what happens is that this kind of product here gets out of control. Either it becomes too big or too small, and you cannot compute any more gradients while training. And the way this was solved was with a different type of recurrent neural network, which is called a long short-term memory neural network, or LSTM. I'm not going to go into the details of this. It looks complicated. It's actually not that much more complicated. What it does is essentially it learns when to ignore an input, when to reset the hidden state, and when to sort of let an input just change the hidden state sort of a lot. So you have all these different gates that regulate sort of how the hidden state is maintained and how much an input can change the hidden state or not, right? And these kind of networks work very well in practice. And they have been used, as I mentioned, in natural language processing. And one of the most sort of, let's say, fun applications of these networks is what is called a char-RNN. It's basically a character-level recurrent neural network where text is fed into this neural network, character-wise, right? One character after another. Like here we have the word hello in a one-hot binary encoding, okay? And we're trying to predict always the next character. And you can train these networks on any text, right? You just take a text and the network just tries to predict the next character in the text constantly, right? And you can train it on that. And what happens if you predict it, for example, if you train it on Shakespeare and you initialize the network randomly and you let it produce, so you initialize the network randomly with a letter, you let it produce the next letter, you take this letter, you feed it back into the network, and you can generate in this way new text, right? It's actually a generative model. And once you train it on Shakespeare and you let it do this, this is more or less what comes out. And if you read through it, it looks very much like, it reads very much like Shakespeare. This is actually a network trained on the LaTeX files of a linear algebra book. And it actually generated LaTeX files, and this is compiled, right? it doesn't make sense, of course, but it looks very much like a algebra book, right? This is actually trained on the Bible. It's a Twitter account, right? Tweets every 4 hours. Yeah, it's called Aaron and Bible. Yeah. This is quite interesting. This is actually a slightly different version of a recurrent neural network. This is a sequence-to-sequence model. So you have basically a recurrent neural network that encodes something that the user types in, and another one that decodes, basically answers based on the encoding, right? So you have a slightly different version of this recurrent neural network, but it's essentially the same architecture, the same network. So you have here the human typing in something, and then the machine replying. This is trained on subtitles from movies, right? And you can see it's a rather philosophical sort of conversation. What is the purpose of life? To serve the greater good. What is the purpose of living? To live forever. What is the purpose of existence? To find what happens when we get to planet Earth. I like the last one. What is the purpose of emotions? I don't know. It's quite cool, actually. This is actually a bit scary for people who work in the coal industry. This is or in the IT industry, actually. In fact, this is a neural network that is trained on help desk calls, right? And this is actually a human making a inquiry about his browser not working, and the network replying what the human should do in this case. And it actually makes sense. It gives actually reasonable advice. Apart from this kind of text applications, we actually use these recurrent neural networks for recommendations, right? To go back into the recommender system sort of area. This is actually a project together with Balázs and Domonkos here. We basically used these recurrent neural networks to do session-based recommendation. What is a session-based recommendation? I mean, you very often have in recommender systems the scenario where you either don't know which user is logged into your system, right? Or which user is using your website. Think of a small sports store, right? Probably when you're buying your ski equipment, you won't log into this small sports store website. You just click on it, you put the items in your basket, and then you go and just order them, right? So this website doesn't know your user ID in some sense, right? So the only thing you have is a session for the user, and the typical way recommendations are served in this scenario is by item-to-item similarity, right? You compute some kind of item-to-item similarity, and this is how you do recommendation. But here's deep learning to the rescue. You can actually train on the click sequences these recurrent neural networks, and it turns out so you have in the input of the recurrent neural network a one-hot encoding of the item that the user has clicked, and on the output you have a one-hot encoding of the most likely item to be clicked next, right? And it turns out if you do that, you get quite massive sort of improvements in terms of recall and MRR, mean reciprocal rank, right? Compared to the item-based, item-to-item-based recommender system, in the order of magnitude of 15 to 30%, right, depending on the metric and the data set. And we actually improved upon this with the use of convolutional networks. So we now not only use the item that is clicked, but we can also use the image of the item that has been clicked as well, right? For more details, we have to wait for the recommender systems, ACM recommender systems acceptance notifications. And we use a particular type of recurrent neural network for this work. We use a gated recurrent unit, which is essentially a slightly simplified version of a long short-term memory network. Yeah, so, and let me just go and talk about the last sort of network, the last type of networks that are currently used in recommendations. And you already mentioned them, the basically autoencoders. Autoencoders are networks that try to predict more or less what they see. Okay, so you can, They're often used in denoising or in data augmentation, right? So if you have some kind of input, basically this autoencoders compute some kind of lower dimensional representation of this input. Using this lower dimensional representation, they then try to recompute the original input, right? So you have an encoder and a decoder there. This is the way sort of it's written. These are the equations for it. And typically, but not always, they try to minimize some kind of squared error loss between the input and the output, right? So it's a very simple method, and you can actually stack this autoencoder, so you can have several layers of these, right? So you have this deep autoencoders, or stacked autoencoders, and they are quite popular in denoising, as I mentioned. So you have the original image, some kind of corrupted version of the image, and you can actually retrieve the very good sort of approximation of the original image just using the corrupted version. And the way this sort of autoencoders are used in collaborative filtering again is actually quite similar to the way the restricted Boltzmann machines were used. And that is, you have some kind of input layer, and in the input layer you add again the corresponding let's say movies that the user has watched, in, if you want, in some kind of one-hot encoding again. And now what you have in addition, I mean that would be enough to do some kind of let's say to build some kind of collaborative filtering model, right? You put a fraction of the movies that the user has watched in the input layer. You try to sort of retrieve them in the output layer. But recently there was this paper published by Wu et al. At Wisdom, 2016, actually this year, where they actually personalize these autoencoders, right? So for each different user, they add this new user node there that sort of biases the autoencoder to the movies that the user actually prefers, right? That's more or less what's happening there. Some kind of bias terms for each user, and this seems to work a little bit better than a normal autoencoder for the task of collaborative filtering, right? So that's more or less sort of what I wanted to tell you about this deep learning on recommender systems. There is a little bit more literature on recommender systems and deep learning available online, but I have to say there's not a lot, right? I would say there's in total maybe 15 papers, currently. So it's still a very open area of research, and I think it's quite an interesting area of research. Right? How do we utilize the power of all these methods for making the recommender systems better? I think it's a very interesting topic. That's why we organize also this workshop. And if you want to sort of play, often people ask me what kind of software can you use for deep learning. Theano is what we are using currently. It's a Python library. Has quite a steep learning curve, but it works. It does the job, right? TensorFlow is getting quite popular right now. There's a lot of sort of push to make it better, and I think currently it's almost at the level of Theano in terms of speed and functionality. Keras is a Python library again that sits on top of either Theano or TensorFlow, so it's a little bit higher level. It's easier to use, more user-friendly, let's say like that. And MXNet is a library that is available in many different languages, right? I think R, Python, Julia, there's more, JavaScript, C++, etc., right? So they have a lot of different interfaces for different languages. Okay, so that's it. Any more questions?
I have to ask you because I see that you have a lot of experience. I personally tried to use Torch, and Keras was a lot of fun because it's Python. Torch was a nightmare.
Yeah.
So how come that you don't use Torch? Because so many people use it. So I thought that.
Well, Torch is in Lua, right? So I didn't, I think it's better if you sort of if you know a language well, you shouldn't sort of diverge from it. And this, I would say 70% of people that use do research in deep learning, use Python. I think so, yeah. I think Lua,
I know it's fairly not.
yeah, exactly. So yeah, we didn't even try. Like, I don't even mention it. You see, I think Torch is a good package. I think the use of Lua makes it not so attractive. Let's say like that. Yeah, that's the main problem, I think. Yeah.
So just some comment to that. I use Torch, and and yes, the Lua is in the beginning is a little bit
Yeah.
kind of I don't know. You don't want to learn like Python,
Oh.
but there are generally two basic tutorials. Learn Lua in 15 minutes. Torch in 1 hour. That's all.
Okay, yeah.
So it's not so.
Maybe.
And I think the learning curve for piano is also long.
Yeah, no, I agree. I think though that, you know, in Python you have all these other tools as well, like pandas. You know, it makes sort of the
Yes.
pipeline of data processing up to the algorithm a bit easier. You know, I think in Lua maybe
Yes.
you probably need to use something else to process your data. And yeah, I don't
That's
know.
all it
You
is.
know, it's a matter of taste in the end as well. You know. So
I just would like to comment
sure.
on your first few sentences when you said that the deep learning goes away a little bit from the original motivation,
Yes.
less similar to the brain or whatever, or
Not-
less similar to computations in the brain. Then we like to have a comment,
Yeah.
a few examples on that.
Okay.
So you mentioned rectified linear units.
Yes.
That corresponds to positive coding
Okay.
by Bengio.
Yes.
The dropout technique corresponds to spikes, and that's according to Hinton and Bengio. Spike-dependent synaptic plasticity, that corresponds to derivation of backpropagation, that's
Okay.
by Hinton. Networks with provable bonds, that's a very recent work, that corresponds to sparse coding, which is typical for the
Okay.
structured sparse networks, that corresponds to columnar organization, that's by me. Ladder network, that shortcuts
I
between
know.
the layers, that is by Volpula. And convolutional neural networks that you mentioned, that corresponds to complexes in the primary visual cortex, and that's by
I know all these things. My point is, let's say like that. I think sort of people were too much focused on sort of what happens in the brain, like in the. First of all, there are two things here, right? One is, I think if you look at these networks and these techniques and all these things, it's quite easy to find something similar happening in the brain, right? Because in the brain, a lot of things happen. The second thing is that in the past, I think, well, first of all, there was a lack of computational power as well, right? But the other thing was that although people build an abstraction of a neuron, right, they still sort of stuck as much as possible to the biological model, right? For example, the sigmoid activation layer is the classical example, right? Once people moved away from that, it became possible to train these neural networks. Like if you put a sigmoid activation layer on a deep network, it's extremely.
activation in the brain.
This
There are
what?
spikes in the brain. That's only positive coding. There's no signal activation in the brain.
That's not. I think the original motivation was biologically sort
The
of.
sigmoid was introduced because it's simpler. And
Well,
also
the linear
it's
activation, the linear,
because
the rectif.
original simplest model
Yeah, the rectified is even simpler, right?
in 1943,
Hmm.
and that wasn't differentiable. So they introduced the sigmoid networks.
Yes, but the linear is even simpler, right?
Linear is even simpler.
Yes.
And rectified is even simpler. And
Yes.
that's positive coding, which corresponds to spikes, which is in the brain. Sigmoid is not in the brain.
I don't know. You know, I think if you talk to Jan LeCun and to Yosef Benju, maybe they have slightly different views.
I don't see
But-
anything else in the brain but spikes.
I'm not, by the way, I'm not a connectionist. You know, I'm not a neuroscientist, right? So,
You know how
but
they communicate with each other.
the
They
The
communicate
neurons.
with each other by spikes.
yeah, of course, yeah.
That's
yeah.
positive coding. There's no negative spike. very hard to
But
create
spikes,
negative
you could look at them as some kind of binary signal, right? So you send some kind of 0 or 1, right? So and there is
That's
work.
still positive. That's not sigmoid. You have to tell the sigmoid.
Mm,
But let's
So the sigmoid is basically, if you look at the sigmoid, it's a smooth version of the indicator function, right? So that's
When you reach some threshold, you shoot, right? You fire.
yes, exactly. So the sigmoid is typically used when you have an indicator function, right? When you want to say, okay, this is 0 or 1, but I want to have something that's differentiable. So I use a sigmoid to make it smoother.
We can continue. Yeah.
Sure. Okay.
No reason.
I know that in Telefonica you use a lot of GPU.
Yes.
with deep learning, but are there any of these libraries already able to use GPUs, or do you develop?
Oh yeah, all of them. Yeah. So let me see. All of them, yeah. All, the ones I mentioned. Also Lua, all of them run on the GPU. You can choose, right, if you want to run on the CPU or GPU, but all of them run. Yeah, absolutely. That's yeah. You wouldn't want to use a single CPU, right? It's almost extremely hard to train these things on the CPU. So it's much easier on the GPU. Yeah.
I know it's a little bit maybe not easy to answer, but how would you emphasize the Rexis challenge in a deep learning manner? I'm pretty sure that somebody in the competition did that.
Yeah. So we actually try something for the. So we try to use basically our what we did here in our work. Something like that, right? Although maybe it's not the most appropriate model, because what we found out is that the click sequence on job postings is very, very short, right? I think about 40% of the clicks on job postings are single clicks, or single clicks or 2 clicks, right? So I'm not sure if it's going to work, but we're giving it a shot. You know, we're not sure yet. So and there are other things we can do here, right? So this is a very simple model. We already have kind of extended this a little bit, but you can extend it in many different ways, right? Here we only predict sort of the item ID of the item that is likely to be clicked next, but you could think of also predicting, let's say, the item features of the item that is likely to be clicked next, right? Or things like that. So there are ways to incorporate, to use, I believe there are ways to use sort of deep learning techniques for the Xing challenge. So we're giving it a shot. I'm not sure if you're going to manage to. We have already a submission. I don't know if we're going to manage to make a more serious one. Yeah, in the end.
What is the size of the network? I mean, on the GRU?
Yeah. So we use hidden states of 500, 500 dimensional, right? We don't. Here we mention embedding layers. We actually don't use embedding layers for the Xing challenge. We actually do, but not in the original paper. We didn't. Yeah, I mean, for this type of network, this is relatively small. It fits in GPU memory, etc., etc. If you want to extend that and add all sorts of different other inputs, like the text description of an item, the image features of an item that come from a convolutional network, you might start getting into hitting some limits in terms of how big your models can get, right? Because you need to have all of your model parameters into the GPU to still keep running fast, right? Otherwise, you don't utilize a GPU if you have parts of them in RAM and parts of them in the GPU, right? Because the copying is too expensive. So, but yeah, I mean, generally what we do is we just use the biggest networks we can afford on the GPU. That's.
So you have many GRU layers?
At the moment, actually, we only use one. Yeah. That's so. Here's the thing with the layers. If you think of layers in feed-forward networks, right, or in convolutional networks, they do this kind of higher order feature extraction, let's say like that, right? They extract more and more complex features at the higher levels. But something very different happens when you stack recurrent neural networks, right? What happens is that the upper layers learn on a different time scale, right? Because they feed on the hidden states of the previous layers, and the hidden states are not so dynamic as the inputs, right? The hidden states change somewhat slower than the input, right? Because the hidden state is influenced by the input, but it's a kind of a, let's say, a product of all the past inputs as well. No? So what happens is that the higher levels of a recurrent neural network learn at different time scales, and that's useful when you're dealing with text, because you want to sort of have first layers build words from characters, and then the second layer maybe it builds sort of phrases from the words, and the third layer builds kind of whole text documents from phrases, etc. Right? So you have this kind of hierarchy there, but because our sessions are so short, right, we cannot really utilize. I think that's the main reason. We don't see any benefit when we add another stack of on top of the single layer, right? So that's the main thing.